Hello, I'm Susan Krumdieck, Professor of Mechanical Engineering, and you have found the Transition Engineering Podcast, where we talk about how to make the energy transition work. All right, we are here today with Johann Land.
Hello.
Yeah, and Johann is a chemical and process engineer from Grenoble University, and then has been doing his PhD at Canterbury University. And so we thought that this would be a very good conversation to have around hydrogen. We've got a lot of popular attention around hydrogen, it seems like at the moment. And so this gives us a really good opportunity to go through the development vector analysis using hydrogen. All right. So in this episode, we're going to go through that. We'll try and keep it, we know you can't see a diagram or keep track of all the jargon, so we'll try and keep it at an even keel so everybody can keep up with us. But here's the premise. We know that you can have a good idea and it can sound pretty exciting and you can make computer-generated images of it. But our question in transition engineering, what we try to do is we match that up with a need, and then we want to analyze what are the hurdles in the research and development of getting from that cool idea to actually a marketable product that can satisfy the need. And each of those hurdles can represent a deal breaker. Now, a deal breaker doesn't mean that the thing can't actually be done. I got the idea. I borrowed it from a TV show called 30 Rock, where there was a funny character, Tina Fey's character, and she writes a book about deal breakers with dates. And so, what's a thing that a guy does that then that's a deal breaker? You're not going to go out with him.
Not doing the dishes?
Yeah, there could be all sorts of things. And so it doesn't mean that the guy is necessarily bad for anybody else or that he doesn't exist. It's just a deal breaker and you're not going to do that. Right? It's just not going to work. So that's where I got this idea for deal breakers. And so what we're going to talk about then is hydrogen for transport. How about we do that for cars? Because that's definitely something, if you Googled it right now, you would see a lot of excitement about hydrogen for cars.
So here our need would be moving people.
Yes, so that's our need. People need to get around. But we're definitely sort of picturing as a substitute for our petrol cars. That's the need we're looking for. We don't want to change what we're doing. We just want to substitute for the petrol cars in a way that does what? Reduces carbon is the whole point, yeah?
Correct, because it's not only a substitute, it would be perceived as a savior.
Yes. So the need then is to provide the transport, but with lower carbon emissions.
If not carbon-free.
That would be great.
Even better.
That would be great. That would be a great story.
Well, I mean, that means we win.
Right. Okay, so if we start at the very beginning and we look at the fundamental prospect of using hydrogen for transport, we have to ask ourselves, are we violating any laws of physics or chemistry in talking about this?
Well, that's the first constraint, the universe, right. The laws of the universe.
So the answer is yes, we would be violating the laws of the universe if we said that hydrogen was going to be an energy source, because it's not. Yeah. Hydrogen is a derived fuel. You have to spend fuel to make it. Yep. So it's like electricity in that respect, that electricity doesn't exist out there that we can just tap it, right? We don't have an electricity well. I mean, we've always dreamed of having some way to capture lightning.
Yes.
But so hydrogen doesn't have a natural source. So if you hear somebody say, oh, there's more hydrogen all around us than we could ever use, well, no.
Yeah, that's that. And it's true that hydrogen is extremely abundant, but it's never present in itself. It's always bound with another chemical like oxygen. That's why we have so much water, for which we can be grateful.
Right.
Or it's bonding with carbon, and that's how we get natural gas, for example. But to get the hydrogen itself, we need to extract it, make it.
We need to basically spend a lot of energy to get it.
Exactly.
So we do actually have a deal breaker right off the bat. If we're going to say that our great idea is to use hydrogen as an energy source that's carbon free, that actually is not true. That's a deal breaker.
Exactly. That's wrong
Okay.
to say that it's an energy source. That's why we would use the word vector.
Okay. So
Energy
shortest
vector.
podcast ever then.
All right, we're done. Credits. Bye.
All right, fair enough. So what we're actually going to talk about then, if we're going to go forward, is hydrogen as a storage for energy, as a way to store energy.
Mm-hmm.
Yes, and if you Googled that, you would definitely find out that that is the story, in fact, is that we're going to use hydrogen to store energy. Because otherwise our EROI is negative on this one, our energy return on energy invested, so it would be a deal breaker. So as a storage for energy, then we'll go forward. So we've cleared our first hurdle then. As long as we're talking about storage, then it's not a deal breaker yet. And that gets us to the next hurdle, which is the materials and the resources that you need. And can R&D get us past that? Which means that right now we've got to start talking about how do you make the hydrogen and how do you use it in a fuel cell to make a cargo. So do you want to start with how you make hydrogen?
Oh, well, hydrogen making.
Well,
right.
I guess we shouldn't say making. That sounds like wizardry.
Okay, let's go to Hogwarts now and let's make some hydrogen. So, it can sound a little bit magical, but no. So, right now, 95%, depends on the source really, of the hydrogen that we are producing in the world comes from fossil fuel. So, we use a process that is called methane reforming or vapocracking. What happens is that we bring some gas to a very high temperature, 1,000 degrees Celsius, so really, really high temperature, with water. And what happens is that it's breaking the hydrogen bonds and we create some hydrogen and some CO2. So this is how we produce right now 95% of the hydrogen in the world, and that's roughly 70 million tons per year.
So we already make hydrogen, so
Correct.
So we could just crank up that production if we wanted to do this.
Correct.
To use it for cars.
That would just mean burning more gas,
Okay.
which defies the purpose of.
So where
having
does
a-
the hydrogen go now then? If we're making that much hydrogen, what are we doing with it?
Oh, for the industry. Okay, well, in terms of industrial usage right now for hydrogen, it's basically organic chemistry. So if you want to have your nice hydrogenated fats for your nice cheap soft bread or something like that, so there you go. Other chemistry industries that need to hydrogenate
Right.
molecules. Some oil refining, you need to
Yeah.
hydrogenate long carbon chains.
My brother works in pharmaceuticals, and they definitely use hydrogen
Correct.
to do. It's kind of like in the kitchen when you're cooking, you need a knife. Hydrogen sort of does that. It lets you
Yes.
slice and dice stuff.
Absolutely.
Now
you
they
can-
need super pure hydrogen though, so they usually use an electrolyzer so that they can get.
which is
super
the
pure.
4 or 5% left of the production, and it's always
But a pill, that's worth a
Yeah.
lot of money. So,
exactly the added value on that is extremely high, so it's totally worth it to make it. And the hydrogen is always produced and used on site. And another usage, very important usage, extremely essential even I would say, is the fertilizer industry.
Okay.
To make fertilizers, you need yourself some hydrogen.
Because fertilizer is ammonia, NH3.
Exactly.
All right. So where do you get the nitrogen from?
The air.
The air. Okay. So
This
it's
one's pretty
sounding like
abundant.
high temperature chemistry to me to get hydrogen
is.
to bond with nitrogen. We're probably going to use some natural gas to do that and some
Yes.
catalysts. I'm sure we're going to need some catalysis.
Nickel,
to get
exactly,
that
nickel catalyst.
and steam. So we got to raise steam. We got to have high pressure. So we got to have pipes with the catalyst in them
Yes.
that are very high temperature and high pressure. And it's probably worth it to make fertilizer because we aren't going to be able to grow crops economically without that apparently.
At least that's not
that's a topic for
right
another
now.
show, apparently.
Yeah, exactly. Right, exactly.
All right, so right now we know that it's worth it in industry to make hydrogen, but then they don't separate the hydrogen out of the stream and put it into a tank to use it later. It's used as it's produced in the chemistry that they want to use it for.
Yes.
Okay. All right, so that's our hydrogen production. If we are then going to use the hydrogen in a fuel cell, I guess we got to start talking about what a fuel cell is. A fuel cell, you're going to need your pure hydrogen on one side. So picture that you've got your 3 fingers, maybe. Hold up 3 fingers. You've got 3 sides to a fuel cell. One is the hydrogen side.
Yes.
The other is the oxygen side, and we need very pure air over there too, and we'll tell you why in a minute. And then in between is what's called the electrolyte. So the electrolyte electrically separates the hydrogen and the oxygen side, and the hydrogen flows into the hydrogen side, and so we need the hydrogen at a pressure that it can spread out over the surface area of the electrolyte. So now picture that you've got 3 pages in a book, so that the whole chemistry and excitement is taking place over surfaces.
Yes.
So the hydrogen comes in and spreads out over the surface, and what does it find when it gets there?
Well, some nice platinum.
Okay, so we need some platinum, and on that platinum, the hydrogen is going to
Split, basically.
Split?
And give off its electrons.
Okay, so why would it want to do that?
Oh, well, because of the platinum. So
Catalyst. So we've
exactly.
got to have that platinum, or
You
the
need a
hydrogen will
catalyst.
just happily be hydrogen.
Exactly, and it has to be one of those noble metals. So we're talking platinum, iridium, palladium. The fancy term is platinoid.
Right, and we can't really just have one piece of platinum. The platinum has to be in direct contact with the electrolyte, so that as soon as the hydrogen splits and becomes a proton, it dives into the electrolyte and diffuses through it.
Exactly.
All right. The platinum also has to be in direct contact with a conductor, because the electron that's given up when the hydrogen splits
Has to go somewhere.
has to go to where we want it to
That's
go.
the whole
to load.
purpose.
That's right. So we have what's called a 4-phase boundary. We've got platinum, we've got the gas hydrogen, we've got the conductor, and we've got the electrolyte.
Exactly.
And that has to be over the whole surface for all of that surface area to be useful. So the idea then is that you spread out the conducting material, usually carbon fibers, to pick up the electrons, but they have to be permeable to the gas. So this is a tricky thing, but it's been kind of worked out. And then the platinum has to be, like we said, in contact with all those things. So the main way to do that is to make it into tiny powders, and sometimes nano powders.
Correct.
So that you have it spread all over the place. And then you got to get those all bound together in a way that they stay together. And this is the first time that I'm going to put up my hand and use the F word. And the F word is finicky.
It is pretty finicky.
I don't know about you, but manufacturing that sounds... I know manufacturing's a later thing, but still, the fact that I have to have those 3 things in contact with each other and the gas freely flowing under pressure is starting to worry me. It's sounding fiddly. Okay, that's the second F word. Fiddly and finicky. We're going to hear those a few times.
It is very finicky. For an engineer, it is kind of a fluid mechanics, electrochemistry nightmare. It's very complex, but
that's what turns us on, though. Come on,
exactly.
That's what we like.
It is really fascinating to look at those systems, how they work, how to make them work, and it's very interesting.
Right.
Lots of physics are involved.
So now I've got electrons running up my my conducting carbon fibers, carbon nanotubes, to a collector around the edge and going off to my load. And I've got my hydrogen ions, the protons basically, jumping into the electrolyte because they're being consumed on the other side of the electrolyte. So let's talk about what the electrolyte is. It's essentially Teflon. It's called Nafion.
It is a fancy Teflon, yeah.
So it's a type of Teflon. Do any of you have experience with Teflon? If you've ever done plumbing, there's a white tape. that is very fun to play with. And will elicit a few swear words as you're trying to use it. But you wrap that around the threads before you put on the fitting, and it will let that release later. So Teflon is very cool. You've probably seen it on coatings on frying pans. It's an extremely cool material. It's in a thin film, like plastic wrap type film. And that is now stretched between the hydrogen gas on one side and the oxygen gas on the other side. All right. So why would the hydrogen go through this Teflon? Because it's been doped with some sodium.
Sulfur. It's basically a sulfur oxide. It would act as a hook, basically, for the proton. And those sulfur oxides would pass on the proton from one neighbor to another until it reaches the other side.
Right, so it's kind of conducted through. So the hydrogen isn't doing anything while it's going through the electrolyte. It's not actually doing anything. It's just going to the other side, being transported, diffusing through. And when it gets to the other side, now what does it find?
Well, again,
platinum. And conductor.
Yes.
And oxygen gas.
You need to have the oxygen. Yes.
Right. Why do we have to have the oxygen? Why not just have it combine up again with hydrogen?
Well, if you're trying to oxidize hydrogen, that's going to be difficult.
But because we want to consume an electron.
Exactly.
Not give one up.
The oxygen will eat up the electron to make
a voltage potential. And there will be a voltage potential now from the hydrogen side to the oxygen side.
Yes.
Because we're producing electrons on one side and consuming them on the other, and that creates a current, which is actually what we use to make things work. Yep. So that's our electric production there. So now we've got, again, we have to have the three things together along with the gas. So the hydrogen ion has to hop out of the Nafion membrane and find a piece of platinum, or it's not going to do anything, and then find some oxygen, and they have to get together and then consume the electron that comes down the conductor. So I'm going to put up my hand and say the F word again. Fiddly, second fiddly. All right. And now it gets even crazier because on that side, we now are going to produce water vapor. And water will stay in a vapor form until there's enough water vapor to nucleate if it's below the condensation temperature. And if we have tiny little channels where we're moving the oxygen across the membrane, and a droplet of water condenses in there, then we get an end to our oxygen moving through that microchannel.
Choke the flow.
All right, we choke the flow. Also, if we're blowing too much air through there so that we don't get droplets condensing, then we can dry out the membrane. The membrane is actually hydrated. So picture, your cornea on your eyeball. It has to be perfectly hydrated in order to work, which is why you blink all the time.
That's a good analogy.
Yeah, it's about like that. It is fiddly. So now we've got a way to produce electricity by consuming hydrogen, basically. It's not going to come back. It's going to go away as water, so it has been consumed. And where did the oxygen come from? It could come from air, but if we use pure air, it can't have any impurities in it, or it will react with other things because we got platinum in there. Right? So that platinum, while it's what we need and it's really good, it also will react with anything else and cause problems.
It would be called poisoning in this case, which is a very known problem when it comes to fuel cells. It's the enemy. So
a lot of fuel cell applications, they'll actually just use bottled pure oxygen instead of trying to get air and purify it.
That's if you want to play it safe, absolutely.
Right.
Otherwise, you need some very good filters.
Well, in our lab, that's what we did, yeah. All right, so that's how the fuel cell works, and as you've heard, it's kind of fiddly. You get a certain amount of electricity produced per square centimeter of fuel cell membrane, of that stack, right. That 3-level stack that you made. And so the way that you build up enough current to make a car go is to put a lot of stacks together. Mm-hmm. You crunch those stacks together, and put in now the delivery of the hydrogen on one side of all these stacks and the oxygen on the other side. And that's a kind of thing that we do in heat exchangers, so with manifolding and that sort of thing. And now we've got to also have temperature control, because the operation range for the fuel cell is a pretty narrow range where it can actually work.
Correct.
So you're going to need to heat up the fuel cell to the right temperature before you even start it. And then once it starts running, it'll actually generate a bit of heat, so you'll have to cool it down. Fiddly again?
Fiddly, very hard to control. It's exactly the same then for battery management or other things, which is what...
exactly the same.
Not the same. It's different, but the idea
it's
remains
challenging.
Similar. It is challenging.
Again, for people like us, for research engineers, R&D engineers, you could spend a lot of money on us getting over this hurdle, because we would do it. There's so many amazing challenges of how to tell what's going on with the fuel cell. Is it hydrated? Is it not? What temperature is it at? Is the gas flowing evenly? And an awful lot of new cool modeling, microchannel flows, yada yada yada. So that R&D channel, getting past that, there has been a lot of money spent on that R&D just at that level of the very basic question of the materials and the resources. And so we do know what the good materials are. They haven't really changed in 20 some years. The winners have been found, or maybe the only ones that would work. So there we are. We'll move on.
I think we can.
Okay, not a complete deal breaker. Very fiddly, but it could be done.
It is just complex, not impossible, just complex.
Okay, and it's going to be a little expensive at this point, but okay. Now, the technology architecture, that's where we got to where we're going to stack all these stacks up, get current collectors on each of the stacks, manifold the gases to flow, deal with making that whole stack the right temperature. So we're going to have some insulation and some heating and some temperature management. It's going to be fun, but we can put our aerospace people to work on that sort of thing. We've got lots of really good engineers. We can come up with lots of ideas here. So that technology architecture is now that you're going to have the fuel cell kind of like a big battery, but now being fed with a tank of hydrogen and a tank of oxygen, maybe with purified air. So you're going to need an onboard air purifier and a way to pressurize the air to just the right pressure so that it doesn't blow your little membranes out of place. And your hydrogen also is going to have to be at just the right pressure to balance the air pressure on the other side. Can all that be done? Fiddly?
Oh, it can be done.
Sure. And it's not the same kind of thing as your carburetor and your injectors. It is definitely fiddlier than that. Or your valves on your engine. Those are sort of grunty compared to what we're talking about here. This is,
True.
Yes. Sort of like curling your eyelashes compared to blow drying your hair, right? One of them is just grunty and doesn't need a whole lot of care, and the other one, you got to be looking at what you're doing really close.
Correct.
Okay, the other thing about the technology architecture that we probably need to talk about is that we're going to have to carry around the hydrogen with us. I reckon. I mean, if we're not going to have like a overhead hydrogen hose connection, we're going to have to fill up a tank and carry the hydrogen with us.
All right.
So we probably ought to talk about hydrogen storage tanks.
All right. Well, let's dive in. Well, you have many standards in the industry in terms of pressure and container in which you're going to store any gas. When it comes to hydrogen, your standard is going to be in the 200 or the 500 pascals range. Pascals.
Bars.
Sorry, bars. That would not be a lot of pressure otherwise. So in that range of pressure. However, hydrogen is very light. Well, it is the lightest gas you could have in the universe. So if you want to have an interesting energy density, you need to have a very high pressure. So if you look at what is interesting for a car, we would be more talking about 700 pascals bars. Again. 700 bars. So you can't just use your usual metal tank. You're actually going to need a polymer composite tank, which is not impossible to make. Again, it's done. I've seen a few. It's done. The pressure, however, is
but it's not really a normal tank or a normal regulator. I mean, we see gas tanks all the time, right?
Exactly.
And we've even got a tank for the barbecue.
Yeah.
Yeah. So gas tanks can't be a big deal. They're a little heavy, I guess. My barbecue tank is a bit heavy.
Yeah, that's your metal right here.
And it has to be strong. What pressure is that? Not 700 bar.
Not 700.
Not even close to 700 bar. Okay, so we are talking about pretty specialist tank. But like you say, it can be done.
Of course.
So it's not a deal breaker yet. And the a way to couple that tank to a compressed hydrogen source that is even higher than 700, because you have to have higher than 700
you
to
need your
fill a tank at
gradients.
700. And then we would need a compressor that can compress the hydrogen to that pressure. And that's where I'm going to put up my hand and use the F word again. Because friction is not our friend here. In compressors are not that expensive, right? You've got one in your heat pump. You've got one in your
fridge.
In your fridge. You've got one in your car, running air conditioner. Compressors are a dime a dozen. It's been figured out how to make them cheap and dirty and pretty darn reliable. But compressing refrigerant and compressing air, in refrigerant, you use the refrigerant itself as the lubricant in the compressor veins. And if you're compressing air, then you have to use a lubricant. And the fact of hydrogen is it does not lubricate itself. So you can't use that, and it will eat whatever lubricant you could possibly put in there.
Correct.
So you need a lubrication-free compressor, which is not a thing that's cheap as chips and readily available. You not only need that, you need multi-stage compression, which means you need multi-stage cooling, compressing, cooling of these at higher and higher pressures. And so this is not going to be cheap as chips. There's just no way. Okay? But it is doable, so it's not a deal breaker yet.
It's still a very big layer of complexity again.
It sure is. And lots of specialist materials in that. All right. Let me just ask one more thing. A lot of times people say, okay, well, that's rare now, and that's why it's expensive. But as we make more of it, then it will get cheaper.
Can that famous scale factor.
Yes, that's right. As we make more of these lubricant-free compressors, they're going to get cheaper. Wow, we'd have to make a lot of them, because the reason that our refrigeration compressors have gotten cheaper is because we not only make more of them, we make a gazillion of them.
Well, that scale factor also only makes sense in an economy, an industry where the energy that allowed to make them is cheap and abundant.
Right. And where the benefit that you get out of it, because my fridge, it doesn't run very often. The compressor comes on every once in a while, does its little job. We get the refrigeration done. And for about, 250 watts every once in a while, I get my food kept cold. So I get a really good service for a little bit of cost. And that's where, as we go forward here and we start looking at manufacturing, supply chains, and applications, we've got to start remembering that we're coming with a lot of baggage already. Yeah, we're coming with fiddliness. We're coming with having to do a lot of really crazy control of the machine while it's running and before it even starts. And we're having to use systems which are not mass produced for anything else that we can piggyback off of. All right, so our next layer then is our manufacturing and supply chain. Manufacturing, this is, you've got to build these components and put them together. And for myself as a researcher, having played with them, I think this is fiddly as. This is really fiddly. Trying to take that Nafion membrane and get it gas sealed against hydrogen, which wants to get through any seal in the universe, and oxygen, which is so corrosive, and we're doing this electrochemistry on catalysts, so whatever materials we're using to make these stacks have to be so corrosion resistant that they're going to be a little bit expensive.
True.
The fuel cell I got in my cabinet here has gold all over it. They've put the gold on it to protect it from corrosion. That's getting a little pricey. All right, so manufacturing wise, do we see a gigafactory yet for making fuel cells? There's a few companies who make fuel cells, Ballard Power Systems being one of them. And you visited one in France.
Exactly.
Where they make fuel cells.
Axen, which is based near Grenoble in France.
Okay.
Which is a sub-company of Air Liquide.
Ah, okay.
So we're not talking a small player here.
Mm-hmm.
Air Liquide being the supplier for the hydrogen, being a gas company, and Axen being the expert when it comes to the fuel cell technology itself.
Okay, so they would know how to handle the gas, so that would
Totally.
kind of make sense that they might go into manufacturing it. All right, so it can be manufactured. Now the supply chains for the materials.
That's where we have to think a lot.
Yeah.
We've already reviewed what it takes to make a fuel cell and how it works. But what about the availability and the production capabilities of those things when it comes to a hydrogen car? If we look, for example, at the Toyota Mirai, which by the way means future in Japanese, because you not only buy a car, you don't just get a car, you get to be in the future when you got such a car, right? So we are talking about just 10,000 cars that have been built over the past 5 years. So of course now there's not just Toyota that is in the game, you also have Hyundai. But still, we would be talking about the same order of magnitudes when it comes to production capabilities. So 10,000 over 5 years again.
Okay, so 10,000 vehicles, and these are usually kind of SUV type vehicles because they've got to carry a big hydrogen tank and the fuel cell and an electric motor and a battery.
Well, yes, if we talk about the specs, the tank itself is a 120 liter tank.
Okay.
When your usual European car, I don't talk about big American cars, those are aberrations, but your regular European car, you would have a tank that is 40 liters for your fuel.
So they're a pretty good sized tank.
Exactly, so you would need to have 3 times the volume. And that would allow you to store 5 kilograms of hydrogen. So now if you want to have an order of magnitude as to how much you can drive with 1 kilogram of hydrogen, it's roughly 100 kilometers. 100 kilometers, 1 kilogram of hydrogen. So that's very easy to remember and do some math. So with that very nice Toyota Mirai, you could do 500 kilometers, which is what they indeed report on their spec list. Now the power of that fuel cell is 110 kilowatt.
Okay.
So
that's a lot of
that's
a lot of power.
That's a nice power. And the electrical battery, the electrical component is just 9 kilowatt. So it's to do what we have explained, this whole thermal management of the battery, because of course if your car is turned off and you leave it outside, you don't want your fuel cell to freeze because the Nafion is hydrated, right? Water is 0 degrees, that's not a very good match. So it's all about that management, and of course you need your radio, you need your AC,
and you need
etc.
to pump the air through the purifier.
Correct. So it's really all the onboard electronics, and it's a nickel metal battery. So
okay, all right.
Very nice engineering, if I was to say.
All right. So how the thing we've talked about so far as material and resources, the Nafion. Is there any shortage of Nafion?
Not that I'm aware of.
Right.
It's really just a polymer. So again, a fancy Teflon. So it's not something that would be a problem in terms of production capabilities.
Well, it's still fiddly to make.
But still now, in
terms
of manufacturing, what was our objective again? It was about transporting people.
We wanted to replace our carbony cars with these lovely hydrogen cars because they only make water in their exhaust.
So how many cars could we make every year then? If we talk about that limit of production, if we look at Toyota again, they have that one factory in Japan. 10,000 vehicles over 5 years again.
Okay.
But let's just crank up the production. Let's fund this and build as many facilities as we can. Let's hire people. We create employment.
Right. Gigafactory. Get
Exactly.
Elon Musk
Let's
in
just
there.
crank up the production. And what would be the limit factor? Because the supply chain depends on so many things. And I would raise my hand here and not use the F word, but use the P word, platinum.
Ah.
So
Well, I got an F word for that. Finite.
Finite, exactly. So we are using this extremely rare resource that is platinum. So price is finicky because platinum can be cheaper than gold, but platinum is way rarer than gold. You mine for gold, you don't mine for platinum. You happen to get platinum by mining nickel and copper.
Sometimes in the right deposits.
Exactly. So it's South Africa that basically has a monopoly when it comes to platinum production.
South Africa, they're our friends, right?
Hopefully, if they want to cut the flow of platinum, then no more.
So how much platinum do I actually need for this car, though? Is it just like a tiny trace amount? Are we worried about something for nothing here?
That's
because I said they're nanoparticles, right? We said they're tiny
they're
particles.
nanoparticles, but
so surely it's not much.
You need a lot of nanoparticles, actually.
Aha.
So
it's called the platinum loading.
Exactly, the platinum loading. So it depends basically how efficient you are. When you're looking at a fuel cell like for the Toyota Mirai, again 100 roughly kilowatt. Let's round up the numbers. We would be somewhere ranging between 50-100 grams of platinum. I give a big scale so that we just have a nice number to play with. It doesn't change the outcome later.
Right.
But we have this 50 grams, 100 grams. That's for one car. Now, what's the amount of platinum that we produce on the planet every year? Turns out we are, if we're lucky, 200 tons. That was 200 tons a few years back. Now, some might say we are on the decline of the production.
Oh. So the platinum that's being produced now is being used for things, apparently?
Oh,
other
yes.
than fuel cells?
Absolutely. We use it for a lot of things. Well,
it's a nice catalyst, right? If you want drugs, if you want chemicals, if you want
if you want to hydrogenate something, you usually do it with a platinoid catalyst. We use it for
so there's a heck of a lot of industrial uses for platinum.
Beyonce would say that. Put a ring on it.
Yep, we use it for jewelry.
Yeah, jewelry. That's a big one. Then we also already use them for cars.
We do.
Yeah.
So that we can all breathe well, yes.
Exactly. You put it in the exhaust.
Catalytic converter.
Exactly.
Again,
that's your
catalysis.
converter.
Right.
But for a converter, we're basically talking about less than 10 grams per car.
But if we're gonna replace all these ICE cars, all these internal combustion engine cars with fuel cell car, then we won't have to make the platinum in the catalytic converters. So you said there's 10 grams in a catalytic converter,
Correct.
and there's how much in the Mirai?
Oh, we would be
maybe 10 times that?
Let's say 70, yeah.
Okay.
Up to 10 times that.
All right, so we'll need to up the platinum production quite a bit then, if we're going to...
Correct. And if we were to just take what we currently have in terms of platinum production, so let's be optimistic and say 200 tons per year, then if we assume, again, just to have nice orders of magnitudes, 100 grams of platinum per car, well, that means we would be limited by physics by a production of 2 million cars per year.
Well, that's a lot.
It is a lot, but then would have to be compared to the over 1 billion cars we have on the planet currently running.
Okay, so kind of replacing the existing car fleet with the hydrogen car fleet is just not a thing. That's a deal breaker, looks like.
It is, and just because of the platinum.
So if you want to talk to going to a world with an extremely fewer number of cars, then we might entertain the hydrogen car for some part of that. Possibly. We'll get to some more questions here, see if there's any other deal breakers. But replacing the way we use internal combustion engine, petrol, carbon-y cars with hydrogen cars, that thing is a deal breaker.
It totally
that can't happen.
Because if you want to replace all of the cars, then you would need decades and decades and decades of production of platinum to reach that production. And sorry, but we do not have that time. The time we have left in order to make a significant difference and win this battle against climate change is less than a century. It's less than a decade. We
Right.
have to do it fast.
Right. And one other little thing on that, I always like to think about the circular economy. The Nafion doesn't sound very recyclable. How about the platinum? Can we take these fuel cells apart and recycle them?
Theoretically, we could, but at what efficiency? That's the question. How much energy do we have to throw in order to recover it? Since it's in the nanoparticles form, in a very diffuse and fine form, that makes the recycling extremely hard. Yes, you do have a lot of platinum in that
Right.
packed object, but in a form that is not very recyclable friendly.
Right. So we do kind of recycle the catalytic converters now.
Correct? That's why they get stolen.
Right. And that's a matter of sort of temperature removal, that sort of thing, separation. But those
Yes.
aren't nanoparticles in that, I don't think.
No, and they're in the middle.
Yeah, they're metal. Yeah. Alrighty. So that's not looking too good. It looks like we've hit a hurdle that we can't get past, but let's keep going anyway, because our next hurdle is applications and system integration. And I think we are going to hit a hurdle here that we can't get past, and I'm going to put up another F word here, and that is fueling station.
Oh.
Because I can go on Google Map and I can put in search for filling station, fueling station, petrol station, whatever you call it in your country. And I can see how many of them there are. And I can just see that, yeah, there's not enough platinum for all of those fueling stations to be making all that hydrogen either.
Correct. Because the hydrogen production also requires platinum.
Right. If you're going to make it from electricity, which was the whole storage idea. We didn't need to store gas. We already had gas. We could put it in a tank.
Exactly. Just store methane as it is. That's
Right.
what we already do for the barbecue.
So there wasn't any point to actually using methane in the first place. That was a dumb thing. We shouldn't have ever started with that. So the whole story is that we're going to use wind and solar and generate the electricity and then use that to make the hydrogen and store the hydrogen, compress it right there. So that's intermittent electricity. Is that the way electrolyzers work? Can I turn them on and off like that?
You can, but it's going to be a problem for the durability of the process.
Okay.
It's the kind of process that is meant to be steady, continuous. Now, if you put in some intermittency in there, it's going to be a very big
It's going
problem
to
for
cost
the
us
durability.
we'll have to do some more R&D to try and get intermittent electrolyzers that can survive.
Which is an ongoing
Okay.
R&D problem. I've had discussions with scientists working at the CNRS in France, and that's how they get a lot of funding. Figure out how to extend the durability of the fuel cells when the current that is feeding them is
You mean the
intermittent.
electrolyzer? Yeah.
Exactly.
Okay.
So now we're realistically talking about a lifetime around above 20,000 hours. So a little bit more than 2 years functioning.
And they're not cheap to start with.
They're not very cheap.
And they've got this platinum in them again. All right.
Yes.
Okay, so that gets us then probably, that doesn't sound good. It sounds like another deal breaker to me. But let's go to the market penetration. That's our last hurdle. Market penetration for personal transport to replace the internal combustion engine. How many people are lined up to buy the hydrogen fuel cell car?
Well, how many people are ready to pay 80,000 euros for a car?
That's what the Mirai costs?
In
So I could
Europe,
go buy
yes.
one right now. So probably there's some people,
Correct.
but there's only 5,000 of them over the last couple of years built, so not that many of them. You'd have to live near a place where you could fill it up. And so the market that we have seen so far for the hydrogen car, for the hydrogen vehicle for personal transport, is in a couple of very distinct areas.
Oh, yes, yes, yes. You can only get yourself a hydrogen car in very specific locations. We're talking about California, Hawaii, Germany, a few places, but it is very
All right,
rare.
so it's kind of a niche-y thing.
Totally.
All right, so I'm going to play another F card here. I'm going to say another F, drop another F-bomb, and that is fad.
Fad, yes.
A fad is a thing that you hear a lot about. It's very exciting. People are talking about it, and yet it doesn't really ever amount to much. It's just a fad.
Like a boys band or something like that.
Yeah, something like that. So I'm sorry, but I think that your hydrogen fuel cell cars replacing internal combustion engine cars, while obviously you can make a fuel cell car.
Of course.
I mean, you can
it's
buy
complex, not impossible.
It doesn't cost $3 million. It costs $80,000. There's other cars that cost $80,000. Now, this hydrogen fuel cell car doesn't do anything that any other car doesn't do. It doesn't give you a new service that you didn't have before, except to satisfy your fad fetish. So let's talk about one more thing. Let's close the loop now, which is, let's say that I did go ahead and do my hydrogen car because I had the money and I wanted to save the planet. And so I signed up and I got the fuel cell car, and maybe even I went and bought an electrolyzer because you can. So I somehow did this. Oh no. So let's say that I did that. Am I saving the planet? Is that the deal breaker here? Because that was the point. That was the idea, was that we were going to save the planet. So if I'm going to take electricity and put it through this whole process so that I can drive, have I saved the planet?
That's a good question. I'd say it is the question. Well, you just have to do the math. Just like for any question, just sit down and do the math.
We like to numerize here in Transition HQ.
Exactly, you have to. You can't solve a problem that you cannot measure. So, how much electricity does it take to produce a kilogram of hydrogen? Well, it's going to be in your 50 kilowatt hour range without compressing. Now, if you were to compress it, you would more likely be closer to 70 kilowatt hour for a kilogram.
Okay.
And then, well, if you just use it directly from your electrolyzer, you don't have to pay the energy for the transport or anything else. But still, that let's say it's 70 kilowatt hour for a kilogram of hydrogen, which is very realistic with the current processes used to do that. So,
okay, that would get me 100 kilometers, you said.
Correct.
All right. So with compression, let's call it 100 kilowatt hours to go 100 kilometers.
Okay, round up, yes.
Right. Didn't I save the planet though? Because I used free wind and solar to do that. Because if I'm using it to make hydrogen, then the people who are producing wind and solar don't make me pay for it, right? Oh, that's tomfoolery. That's not the way that works. Okay, so I could buy 100 kilowatt hours of electricity to go 100 kilometers. I think that I could move about 100 people with that 100 kilometers if we used a train. So maybe 100 times less efficient than if we all went together in a tram or train. And I think that I would use only about a third of that if I just used a battery and had an electric vehicle. Am I right?
I don't have the
numbers to hand. But I think, as with many things, the idea and the story and all those parts, we start to see now where it does start to fall apart. And while it would be really fun to work on it in R&D and to dream about it and to look at stories about it and to share links on Facebook about it, we're really going to have to look in another place, in another direction for what we mean by energy transition. You agree on that?
Totally. What is the objective again?
What is the actual objective?
If we work with a realistic constraint, which is the Paris COP21 agreement, then what does it look like actually lowering your emissions
to
by a
reduce the
4
carbon.
factor,
That's
yes,
the
by
point.
2050.
Right.
4 times
And
less.
we don't think we've actually done that by all of this. And besides, it just doesn't work the way we think it's going to work. So, I think there's a few deal breakers in that one on the hydrogen. And for me, then, I'm just going to work on something else. If people want to work on hydrogen fuel cell cars, that's fine. But I think it would be a good idea if everybody understood what the limitations are and that we're really not talking about saving the planet when we share a story about hydrogen trucks or hydrogen trains or hydrogen cars, because the same story applies for all of them.
Correct.
And we really need to get on with what we really are going to do. Fair enough?
Sounds
all right.
like a good deal for me.
Thanks, Johann. And we will catch up with some more deal breaker analysis in the future.
With pleasure.
Bye.